Hi, I'm Mark Mellors, and along with Rob Berwick, we've built Tauradigm, our entry into Pi Wars. In this video, I'm going to concentrate on how Team Tauradigm approach the Eco Disaster Challenge, where you have to get barrels like this into the appropriate zones depending on their colour. To break that down, the general approach is to find a barrel, pick it up, decide on its colour, navigate between the other barrels and get it to the appropriate zone, and then turn around and repeat that process. As a team, we thought that navigating between the barrels could be quite tricky, especially as if you move a barrel, picking up the next barrel will become more difficult where you have two barrels close together. So we're taking the alternative approach of picking up a barrel and then storing it on the robot while we go and pick up the other barrels. And in that way, we don't need to navigate between the barrels, we can just pick up the nearest barrel and then get it to the appropriate zone and deposit all the barrels that colour into that zone. One drop off per zone. Much less travelling. Hopefully quicker. However, that requires a much more complicated attachment, which is why we've got this massive thing and this complicated robotic arm. So to break it down, how are we picking up the barrel and moving it to the right place? So to find the barrel, we're using a different strategy to other teams. We have a lot of experience with computer vision, but it's very difficult to get right and tune. So we're actually not using the camera at all to find the barrels. We're going to use our distance sensors. We have an array on the front of the robot which should allow us to see the nearest barrel and drive towards it. The robot doesn't actually care what colour the barrel is. We just find the closest barrel and drive towards it. We have a wide grabbing arm that allows some tolerance to how we pick it up. And then once we've captured that barrel, the grabber itself has a colour sensor that tells us what colour it is. That allows us to choose which storage system the barrel gets deposited into. So we thought we'd take the approach of collect all the barrels, sort them on the fly into their two colours, and then deposit the barrels in one go. So for that, we have this storage cartridge. So the barrels get dropped into there, and we can store 6 barrels per cartridge. And these are going one per side on the robot. So we're going to have the red side and the green side. And then once this is full, and we've collected all the barrels, we use the rack on the bottom to unload the module and deposit it in the appropriate location in one go. That's the theory. You see, this contraption has got quite big. We're actually hitting all of the maximum limits on Pi Wars. So 2 of these side by side is within a few millimetres the maximum allowable width. With the grabber back in its collecting position, we're on the maximum length within a few millimetres. When the arm is forwards and it's most articulated, we're closest to the maximum allowable length for articulated appendages, and similar is true for the height. Storing 12 barrels within the Pi Wars space constraints is very challenging, but we think we've managed it. So how do we know what is a barrel and what is the wall? Well, since we've got an array of sensors, we can see it at 6 different points along the front of our robot. The walls of the arena are all straight. It's basically a square. So anything that sticks out, so has something further away from either side of it, must be a barrel. There are no external corners on the arena. So we can find that external corner, or a point that's closer to us than either side of it, turn towards it and drive towards it. Once we've collected all the barrels, how do we find the drop-off zones if we're not using a camera? Well, this is where our localization comes in. We're using something called Monte Carlo localization. So initially we have a model of the arena. We have a mathematical map of the arena that has the walls in it, and we fill that with an array of points. In each one of those points we move according to how our encoders say we have moved in terms of forward distance, and our magnetometer or IMU tells us in terms of heading. So we move all the points in the way that we know our robot is moving. Now, if our movement was exactly tracked, we would only need one point. We would put that point at our known start position and we could just keep moving in the direction we know we're moving, and that would give us our current position and therefore our current direction required to get to the final drop-off zone. However, the magnetometer is not perfect, the encoder is not perfect, the tyres slip, so we need something else. And that's where the Monte Carlo element comes in. All of the particles represent all of the possible places the robot could be. Combined with our distance sensor readings, we know how likely it is that any given particle is where we actually are. We compare the probability of those particles having the same readings as the current robot is reading with distance sensors, and we weed out the unlikely particles. Any likely particle we duplicate and put another particle near it. So the swarm that initially covered the whole arena condenses down to where the robot probably is. And you can see on this animation we have a swarm moving around that is actually quite condensed and sufficiently accurately predicts where the robot is. Before we start the challenge, we will calibrate our map so that its north-south alignment agrees with the actual arena. Then we will know where on that map the actual drop-off zones are in terms of north, south, east, west corners or sides of the arena.